Today we're going to continue with determinants. We're going to learn some important properties of determinants, and we're also going to learn another method for calculating determinants of matrices that is more computationally effective when you have a large matrix. As we mentioned, if you try using the combinatorial approach, where you're looking for all possible ways of how you can multiply numbers in rows and columns, in general, the amount of multiplications you have to do is a very large number if you have a large matrix. The exceptions is when you have a matrix that has lots of zeros, but otherwise there's a lot of operations to do to get an answer. So today we will learn a computationally effective way that you can use for larger matrices. So let me quickly begin by reminding you what a determinant is. So we start with a square matrix. Determinants are defined for square matrices. So you start with a square matrix. And the determinant of the matrix, this is the way we defined it. The determinant of the matrix is, there's different ways to say it, but the determinant of the matrix, and this was by definition, this is the way we defined it. So you take the columns of the matrix, you take the first column of the matrix, you take the second column of the matrix. So you take the n columns of the matrix. So these are your vectors, the vectors that come from the columns, and then you calculate the oriented volume of that. So this is the volume, this is the oriented volume of the columns. This is the oriented volume of the columns of the matrix. You can also do it with rows. Let me make this comment. You will get the same computation if you use rows instead. So we'll talk about why that works later on, but I just wanted to mention this here, that if you decide to use the rows instead, so if instead you decide to use the rows of the matrix, so if you look at the first row of the matrix, the second row of the matrix, so if you use the rows, if you take the vectors coming from the rows, you will actually get the same answer. So what it has to do with is, so the reason why you will get the same answer if you use rows or columns has to do with the simple fact that that the determinant of the matrix and the determinant of its transpose are actually the same thing. I will give you a justification for this later on, but I just wanted to state for the time being that if you have a matrix and you take its transpose, the matrix and its transpose will always have the same determinant. So that's just a nice fact to know. And because of that, whether you're thinking of the columns or whether you're thinking of the rows, that's what the transpose does. It interchanges columns for rows. And if you do the same calculation using the rows, you would get the same answer. It's not immediately obvious, by the way, why you're supposed to get the same answer. Because if you take the rows of the matrix and you write out this volume form, you're calculating the volume of a different set of numbers. So it's not completely obvious why you're supposed to get the same answer. It's not immediately clear. You have to give some kind of argument for that, why it always works out the same way. But we will give an argument for this, and you get to see why this works. But what I wanted to do for the time being is talk about what happens with the determinant under row operations. So let us discuss what happens with the determinant when you apply row operations to a matrix. Now, we know that there's 3 row operations. So let's talk about what happens for each row operation. So the first row operation is you can swap two rows. That's the first row operation. Another row operation is you can multiply a row by a non-zero scalar, a non-zero number. And the third row operation is you can add a multiple of a row into another row. And here are the facts that we need to know. Let's talk about the effect of this. So when you swap two rows, this actually has an effect on the determinant. So this operation, this row operation, will change the sign of the determinant by -1. Okay, so if you have a matrix and you take two rows of that matrix, or by the way, two columns as well. I mean, if it works for rows, it also works for columns. That's what we were saying earlier. We were saying that whatever you do with the rows, it also works for the columns. The reason why I'm suddenly talking about rows is because we're used to doing row reduction, not column reduction. You could technically do something called column reduction, but the way we learned it is by doing row reduction, so we'll just stick to doing it that way. If you swap two rows, you get a different matrix. And the matrix that you get will have a change in the sign of -1. That's what happens when you swap two rows. If you multiply a row by a non-zero scalar, then this will multiply the matrix by a factor, by the same factor. And finally, property 3 says that, and this one does not change the determinant at all. So let me do a very simple example that illustrates all three row operations and the effect it has on the determinant, and then we'll explain why it works like this. So let's start with this matrix over here. So I'm just going to do a 2 by 2 matrix because I think that is good enough. Let's suppose you have the matrix 1, 2, 3, 4. And we know that the determinant of this matrix is equal to 4 minus 6. So the determinant of this matrix is -2. Yeah, that's what it says. It will multiply. Yeah, it will multiply the determinant. Yes, thank you. It will multiply the determinant by the same factor. Thank you for the correction. Okay, so that's the determinant of A. Now let's suppose. So let's see what happens. So if we swap the first two rows, we get, so here's what happens if we swap it. We have 3, 4, 1, 2. And now the determinant, if you do it, it's now going to be equal to 6 minus 4, which is 2. It's +2. You see, you had a sign change. You had a negative over here. You have a positive over there. You have a sign change. Okay, so this illustrates the first one. Let's look at part 2. Part 2 says that if you multiply a row by something, then the determinant will get changed by the same factor. So let's suppose we have 1, 2, 3, 4, and we multiply. It does not matter what row you multiply. Let's suppose we multiply the first row by 5. So the first row got multiplied by 5. So if you do that, you would end up with the matrix 5, 10, 3, 4. And now if you do the determinant, you would get that this is 20 minus 30, which is -10. Now, what's the significance of -10? Well, negative 10 is, so it would be negative 2 multiplied by the same factor. So it gets negative 10 multiplied by a factor of 5. So the same factor that you use to multiply the first row is the same factor of how your answer changes. And it does not have to be the first row. The same thing works for the second row. Now, the third row operation does not change anything at all. So let's actually see why that is. So let me say it like this. So if we take the first row, so let's write it like this. Take row 1 and take row 1, multiply it, let's say, by 2 and add it into row 3. And we get the matrix. So this is the matrix we will get if we do that. So let's do that row operation. So if we do that, then the first row stays as 1, 2, and the second row, that will become 2 plus 3. So this would be 5, and that would be 4 added to 4. That would be 8. Okay, and if you take the determinant of this, you would get 8 minus 10, which is negative 2. It's the same answer. It does not change. Nothing changes here. So these are the row operations. And by looking at these row operations, what you notice is the best row operation for working with determinants, it's the third row operation because it does not change anything. The first row operation, it's not as bad. It does change the answer, but it changes the answer only by negative 1. And the second one is problematic. The second one actually changes the answer by that multiple. So here's the idea. So the idea is that if you have a matrix and you want to calculate its determinant, you use row operations. You try to use only the third row operation to fill up the matrix with as many zeros as possible. Because we know that the more zeros you have in the matrix, the easier it is to find the determinant. And then maybe sometimes you might need to use 1 to flip rows. But you will always completely avoid using 2 since it changes the answer. Now, if you use row operation 1, then you should keep track of how often you flip rows. Because every single time you flip rows, you're going to change the answer by a negative sign. So the idea is you mainly try to only use the third row operation as much as possible. You actually had a homework on this. There was a homework assignment on this that we called it row reduction without division. You probably recall doing it, and I mentioned that this is a type of row reduction which is very helpful for calculating determinants, and we're going to use it today and see how it will help us solve these problems. Now, before I do an example with you of how this is being used, let's actually explain why these 3 properties work. Let's explain why this is the effect that you have on the determinant. And it all comes down to this. You have to go back to the definition of the determinant. And for simplicity, let me just do it for a 3 by 3 matrix. So for simplicity, let us just do it for a 3 by 3 matrix, though the argument works in general. It's just easier to write out because you only have 3 things. well, once you understand why it works for 3 by 3 matrices, you will see why it works for any matrix. So let's start with property 1. So the determinant of a 3 by 3 matrix, you have to calculate the volume. So the three-dimensional volume, either of its rows or columns. So we're going to use the rows here. So it's going to be the first row. You're going to create a vector consisting of the first row, the second row, and then the third row. And you're going to calculate the oriented volume coming from the rows. So that's what you're going to do. Now, let's see what happens if you swap two rows. So if you swap, say, row 2, row 1, and row 2, then the determinant changes as follows. Will change into, so what's going to happen with the determinant? So then the determinant is going to go like this. You're going to have the oriented volume of row 2, row 1, and then row 3. But now you have to recall the alternating property. So now, by the alternating property of oriented volume, as we've talked about, this computation will be the negative of the previous computation. Because the alternating property says that if you take any two vectors, let's suppose the first two, and you swap them, what kind of effect will you have on the volume? The volume will become the negative of what it was. And so the new determinant will be the negative of what it was. Okay, now let's explain property number 2. Why does property number 2 work? Well, the reason why property number 2 works is if you were to take a row and you were multiplied by a constant, so let's suppose we multiply the second row of the matrix by a constant. So now you have a constant here. Now we mentioned one of the properties of oriented volume is that if any one of these vectors gets multiplied by a constant, you can end up factoring the constant out. And so what you're getting is that the volume of this new matrix, it's the volume of the old matrix multiplied by the same factor. So the determinant gets increased by the same factor. And then finally, the third one is the most interesting one. Why is it that it does not change? So if you add one of these, if you take one of these and you add it as a multiple into another one, then the answer does not change. So this one's a bit more interesting. So suppose we add, let's suppose, 3 times row 1 into, let's suppose, row 2. Let us see what happens. And we're claiming that no changes will actually occur. You will get the same answer. So let's see that. If we add, so we take the first row. We're going to take the first row. We're going to multiply it by 3. And we're going to add it into the second row. And everything stays the same as before. We're claiming the answer does not change. And the reason why the answer does not change is you have to use the distributive property. So use the distributive property to get, and something interesting is going to happen when you use the distributive property. So we would get, if we do that, we would get V3 of row 1 of A, comma 3 row 1 of A, comma row 3 of A, like that, and then plus V3 of row 1 of A, comma row 2 of A, and then comma row 3 of A. That's what we would get. But now, here's what we need to notice. Well, first of all, the 3 can be put, I mean, you can just put the 3 over here. So you can just put the 3 right there. So you really have this. Now look at this. You have a repetition. there's a repetition in the vectors. There is a repetition in these vectors. So this entire computation is automatically 0. Without even doing the calculation, the fact that these vectors are repeating, we know that's equal to 0. And look at what we are left with. We're left with the exact same thing that we started with. So we started with the determinant of the matrix, and after doing this row operation and calculating the determinant of that, we end up with the same exact calculation. So it's because of that the third row operation property does not change the determinant of the matrix. And now let's do an example. So let's do an example of where we calculate the determinant of the matrix by using this kind of process. So let us do an example of a large matrix where we use row operations to find the determinant faster than just by looking at various product combinations. So the matrix here would be the following matrix. So the matrix here would be 1, 2, 3, 4. As you can see, I'm not being very creative in how I come up with these matrices. I like to just use the same numbers again. 4, 3, 2, 1, 3, 1, 2, 4, and then 1, 2, 4, 3. Okay, this is a 4 by 4 matrix, and we're going to find the determinant of this. Now, the combinatorial method, let me make a comment here. The combinatorial method is tedious because it will involve 4 factorial, which is 24, right? 4 factorial is 4 times 3 times 2 times 1, which is 24 possible combinations, possible permutations. So the way you do it is, it's up to you whether you want to do it with rows or columns. Last time we did it with columns, but you can also do it with rows. So you can divide this into rows like this, and then you have to look at possible combinations. So for example, you can take 3, you can take 4, you can take 4, and you can take 2. You have to make sure that they're coming from different rows and columns. And then you have to multiply these numbers together, 3 times 4 times 4 times 2, like this. And then you have to determine the correct sign. Is it plus or minus? How do you determine the correct sign? Well, you have to determine how you're choosing the numbers in the row. So this was the third number in the row. This was the first number. This was the third number. That was the second number. And then you have to determine whether that particular permutation is positive or negative. We're not going to do that because that's what we did last time. And that method here is not very effective because it takes too many combinations. 24 is not that bad, but if you had a larger matrix, like 10 by 10, that would be like almost impossible to do. That's just too many combinations. So instead, what we will do is, instead we will use row reduction without division, and trying to avoid row swaps. The reason why we're trying to avoid row swaps is because every time we do a row swap, our answer will change by a negative sign. So we try to avoid doing that. Though sometimes we have to, if we have a 0 and we have to move the pivot. So sometimes you have to, but you try to avoid doing that if you could, and get an answer. So you try to use row reduction, and we only need to reduce the matrix down the diagonal. In other words, we want to get an upper, what is known as an upper triangular matrix. If you're not sure what I mean by an upper triangular matrix, you will understand what I mean by that as we do the calculation. And you again see the benefit of row reduction. Row reduction is really the only computation you ever do in linear algebra. Even determinants is row reduction. Everything you do, every calculation in linear algebra is row reduction. That's why we talk about it on the first day of class. So row reduction, we have a 1 in the upper left corner. I'm going to do this rather quickly because I assume everybody knows how to do it. I'm going to do this rather quickly. So we have a 1 in the upper left corner. We want to fill these with zeros. So the way we do it is we multiply the first row by -4. -4, -8, -12, -16. Multiply the second row by -3. -3, -6, -9, -12. And then just take the negative of this row. -2, -3, -4. And when you do that, the new matrix that you get, the reduced matrix, the more, well, not technically, it's not yet reduced, but the more reduced matrix would be this. And then this would be -5. This would be -10. This would be -15. This would be 0. No, I'm sorry about that. That's not 0. That's -5. That's -5. This number over here is a 6, not a 1. So that's -5. This is -7. This is -8. And here we have 0, 1, -1. So that is what I'm getting when I do that. Let me know if you notice any silly mistakes, but that's the way it's looking right now. So let's highlight the pivot, pivot, pivot. Usually when you do row reduction, you turn that number into a 1, but we're doing this without without division. We're just going to keep it as it is. Okay, so we want to turn this into a 0. So we just add this in. So this would be, you're going to add the negative of that row. That would be 10. This would be 15. And now if we do that, we will end up with 1, 0, 0, 0, 2, -5, 0, 0. Then we have 3, -10, 3, 1, 4, -15, -8, -1, like that. Okay, we have this. And what we do next is, so you could flip these two rows. The temptation is to flip these two rows because after all, you have
-7, not negative. Wait, yeah, 7. The -8 is 7, right?
Okay, thank you. Yeah, thank you about that. Thank you. Any other mistakes? No other mistakes here?
Okay. No, I think everything else is good.
So, all right. So what you need to do is you need to turn this into a 0. Now, usually what you do is you multiply the second row by a third, and you turn that into a 1. We're going to avoid doing it. Now, you could swap in the last row in here, but if you do that, then you cannot forget that you did a swap. So your answer is going to change by a negative sign. I just want to show you what happens if you do not swap anything. So to put a 1 over here, what you really have to do is you have to take row 3, you have to multiply by -1/3 and add it to row 4. So if we do that, this would be -1, this would be negative, so 7 times minus a third. So 7 multiplied by minus a third is negative 7 over 3, like that. So that's what we're doing. You see, the pivots are being left alone. We're not turning these pivots into a 1. We're just leaving them alone. And by doing that, we end up with 1, 0, 0, 0, 2, negative 5, 0, 0, 3, negative 10, 3, 0, and then 4, negative 15, 7, and this one's a little bit of a small computation, so that would be negative 10 over 3. Okay, that's what we get. And this is what we call, and then we stop. So stop the row reduction process here because you got, and it's called an upper triangular matrix. All of the non-zero numbers are above this triangle. You see you have this triangle over here. You have that triangle. The determinant of a triangular matrix, of an upper triangular matrix, is easy to find because there's only one combination of products that works, and that is just the diagonal. So the determinant of this matrix, if you do it, you multiply the numbers on the diagonal, which is 1, negative 5, 3, and negative 10 over 3. And if you multiply those numbers out, you will get 50. The determinant is equal to 50. And you can see that was pretty quick. We did not have to look at combinations. I just want to explain one more point. I mentioned this on Tuesday, but why you just have to multiply on the diagonal? Because it has to do with, if you look at the possible combinations, you will notice there's only one way to do it. If you, for example, end up cutting up the matrix into 4 columns, there's only one possible number you can pick in the first column. There's only one non-zero number. If you pick a 0 number, there's no point because you're multiplying by 0. You're going to get a 0 answer. This is a non-zero number. Now in this column, you already picked a 1. You cannot pick a 2 to multiply it with it. You have to make sure the basis vectors are chosen to be differently. So you have to force to pick a 5. And now if you pick a 1 and negative 5, well, you cannot pick these 2 because those 2 rows have been used up. So you're forced to pick 3, and now you're forced to pick negative 10 over 3. So there's only one possible combination of products that works, and it's just the numbers on the diagonal. And if you multiply it out, that's the answer that you get. So that's how you do it. I think one answer, I think one example is good enough, because as you can see, this is just row reduction. If you know how to row reduce, you know how to do it. So you basically do row reduction down the diagonal. There's no need for you to go back up. You can do that, but that's unnecessary work. Just go down the diagonal. So technically it's half of the row reduction, and you just avoid dividing out your pivots to turn them into the 1. You just leave them alone as they are. And if you do that, multiply the numbers down the diagonal and you get your answer. Now, if you swap 2 rows, then the answer changes by a negative sign. So for every swap you do, you have to change the answer by a negative sign. So if in this row reduction process you do 4 swaps, then you have 4 negative signs, which is a positive sign. So this is the reason why it's generally a good idea to try to avoid doing row swaps as much as you can, so you do not have to keep track of that as you're doing the calculation. Now, let me move on to properties of the determinant. So there's some important properties we need to mention. So properties of the determinant. Some important properties of the determinant. Let me start with this one. So say that A and B are square matrices. So you have two matrices that are square, and both of these matrices are the same size. Then there's this very nice property. If you take the determinant of the product of two matrices, then that is the same thing as the product of the determinants. And I'm going to give you a geometric proof of this fact. The geometric proof of this fact is very elegant and simple. Trying to prove this algebraically is not so easy because the determinant of a matrix is this complicated, convoluted expression of various products, and the matrix product of two matrices is a very complicated operation as well. So it's like you're having these two complicated operations, matrix product and determinant, but somehow they're nicely compatible with each other and they work out. If you try to do this algebraically, that would not be the easiest way to do it. But I'll give you the simplest proof I know of this is a geometric proof. And it has to do with this. So let us think of these matrices, A and B, as linear maps. Matrices give you linear maps. So you have linear maps from Rn to Rn. So both A and B act on n-dimensional space and transform it in some way. Right? You have a before and after picture. We've done plenty of examples with two-dimensional pictures, but in general, you have an n-dimensional linear map. The determinant, so recall, the determinant of a matrix measures the spatial distortion factor of the linear map. And furthermore, recall that matrix multiplication is, we say, the composition of two linear maps. In other words, one linear map followed by another linear map. So think of it like this. Suppose the determinant of A is equal to 2, and the determinant of B is equal to 3, let's say. And what does that mean? So that means A acts on Rn and distorts space by a factor of 2. And B acts on Rn and distorts space by a factor of 3. Then AB, this is matrix multiplication, the product of the two matrices, will be the net effect of one linear map followed directly by another linear map. So if I draw some pictures, maybe this will help clarify what we're saying. I'm just going to draw two-dimensional pictures because they're just easier to draw. So we have R2, okay? I'm going to draw R2 again. I'm going to draw R2 again. So let's suppose you have some kind of picture. Maybe you have, I'm not sure, maybe you have a right triangle, let's suppose. You have a right triangle, and then you act on this right triangle by A. So you apply A to this right triangle. Now, because the distortion factor is 2, it means you're going to have a spatial distortion. If the determinant is 2, that means this triangle will expand in size by a factor of 2. It does not have to be a right triangle. Maybe the angles change, but the size will become twice as big. So maybe you will end up with something like this. Maybe you will end up with a triangle. It's not going to be a right triangle anymore. Okay, it's not going to be a right triangle. It maybe will look something like this. Maybe the angle changes, something like that. So if the area, so if you have an area, let's say the area over here was 5, let's say. Well, let's say the area is equal to A. So the area of this triangle is equal to A. Then the area of this new triangle is now going to be 2A. That's because the determinant will distort the image, right? The before and after image. The after image will grow by a factor of 2. Now, if you apply another linear map to that, so if you take that image and you apply B, well, what's going to happen? That triangle is going to grow again by a factor of 3. So maybe this triangle will turn into something like this. So maybe what's going to happen is, this is a possibility, maybe these two sides, the angle between them will shrink or something. So maybe you end up with something like this, perhaps. I mean, that's something that could happen. These distortions, they do not have to preserve angles or anything like that. I mean, we've seen examples on the homework where the edges might become slanted or something like that. But the whole point is that the actual area, the growth factor, will get increased by a certain amount. So if this area is 2A, then the area of this new triangle, this is like the before image for B. This is the before image, and after you apply B to this region, it now becomes 3 times as big. So now the area over here would be equal to 6A, because you're multiplying this one. You see, you're multiplying this one by a factor of 3, so it now becomes 6A. But what is matrix multiplication? Matrix multiplication on a deeper level is what happens when you follow one linear map by another linear map. You do one linear map followed by another one. So if you go directly, if you do matrix multiplication, if you do A times B automatically, then the matrix multiplication of A times B sort of skips this middle step. So if you take these two matrices and you multiply them together, well, technically, I should write it like this. A goes first, right? A goes first, and then B goes second. So maybe I should write it like this, BA. So you apply A. It's the same thing as the way you write functions. The function that goes first is, so you apply A, and then you apply B. So this is going to be the effect. So if you do matrix multiplication, this is going to correspond to the linear map that is taking this image and it's sending it to that image. But look at what happened to the area. The original area was A, and now the new area is 6. You see, and where's that 6? It's really 2 times 3. That's what it is. It's the product of these two. The product of these two is going to tell you what the net effect would be. And that's like the nice geometric proof of this. Like if you think about it geometrically, it should make sense why the determinant of AB is equal to that. I should notice that you might say, well, we've written determinant of BA. It really does not matter. So even though this is not commutative, the right-hand side is commutative. So, I mean, if you write it like this, determinant of BA, you would get that this is the determinant of B times the determinant of A, but that's the same thing as the determinant of A times the determinant of B. So even though matrix multiplication is not commutative, these are no longer matrices. These are numbers. These are just numbers. The determinant of the matrix is not a matrix. It's a number. And because these are numbers, you can rewrite them in this kind of an order. That's okay. So this is the geometric justification for this very nice and important property, that if you multiply two matrices together, the determinant of their product is the product of the determinants. Let's also say something about invertible matrices. That's another important property. Let us say something about, so let me say it like this. So related to this multiplicative determinant property is the invertible matrix property. So it says this. Let's state it as a theorem. So it says this. So if A is invertible, so invertible means the matrix has an inverse, then the determinant of the matrix is not zero. And it also works the other way around as well. The converse is also true. It says that if the determinant of the matrix is not zero, then A must be invertible. So let me explain why one is true. And I'm going to put part 2 on the homework. Part 2 requires a different kind of argument. You would think that they're almost identical statements to each other, but the arguments are a little bit different. The first one is easier to show. The second one is harder to show. So I'll put it on the homework for you to think about, and I'll give you a hint of how to approach it. So let us justify part 2. The justification here is actually quite simple. So since A is an invertible matrix, there is a matrix B such that AB is equal to the identity matrix. In other words, B is the inverse matrix. You want to say it like this. Invertible means you can find the matrix so that the product gives you the identity. So since AB is equal to the identity, it means by the property that we just discussed, the determinant of A multiplied by the determinant of B is equal to the determinant of the identity. Now, the determinant of the identity is 1, because the identity matrix, it's a diagonal matrix. It's for the same reasons that we said before. If you have it's both an upper triangular matrix and a lower triangular matrix. But when you have a triangular matrix, the determinant is just the numbers on the diagonal. Now, a geometric way to see this, by the way, if you want to give like a geometric proof why the determinant of the identity matrix has to be 1, think of it like this. The identity matrix is the identity linear map. It's the linear map that does not do anything. So if you take space and you do not do anything to that space, what's the distortion factor? It's 1. The before and after image, not only does it remain the same in size, it actually does not move at all. So that's why it's equal to 1. That's another way how you can see it. So you have a product of two numbers is equal to 1. So therefore, the determinant of this matrix is not equal to 0. There's no way it could be equal to 0. If this is equal to 0, then, 0 times anything is 0. It's not equal to 1. So in fact, what we see is that we can say a little bit more than that. We can say that the determinant of B, so if you solve for B, the determinant of B is 1 over the determinant of A. So you're saying that the determinant of A inverse, because that's what B is the inverse matrix, is equal to, you can say it like this, it's the determinant of A inverse. That's what we're saying. You see, it's 1 divided by the determinant. So if you take the determinant of the matrix, it's the same thing as taking, if you take the determinant of the inverse, that's the same thing as taking the determinant of me and then taking the inverse of that. But we really have to understand, it's kind of funny, but there's two different inverses over here. This is a matrix inverse, whereas this is a number inverse, because the determinant is a number. So one of them is an inverse of a matrix, the other one is an inverse of a number. But notationally, the notation just works out just fine. So that's the property that I wanted to mention. Now this property over here, that if the determinant is not 0, then the matrix must be invertible, that takes a different argument. It is trickier. I will put it on the homework for you to think about. I'll give you some hints to how to approach it. But I want to make a comment here about this theorem, because there is students sometimes misunderstand this theorem. Common student, I'm going to say mistake in quotation marks. It's not really a mistake. It's more of a non-requirement in many problems. So this is like a common mistake is students do this. So you have an exam problem. So the exam problem says, given matrix A, calculate the inverse of the matrix. And then the student does the following. The student spends 10 minutes calculating determinant of A, then says, since this is non-zero, the matrix is invertible, and then spends like 15 minutes calculating the inverse of A by row reduction. Now, the reason why this is completely unnecessary is because you can completely skip this part. If you calculate the determinant of a matrix and you find that the determinant of the matrix is a non-zero number, how does that help you actually find the inverse? It does not. It does not actually tell you how to find the inverse. The way you find the inverse of a matrix is by using row reduction. Now, if I give you a matrix and I ask you to find the determinant, usually the easiest way to do that is also using row reduction. So think about what you're doing. You're using row reduction to calculate the determinant. If you find that the determinant is non-zero, that does not actually help you get the answer. And then you have to do a completely separate calculation to then find the inverse of the matrix. So it's like you're doing a completely unnecessary step to solve the problem. If the problem says to calculate the determinant of the matrix, then you do that. But if a problem says to find the inverse of the matrix, you just immediately start finding the inverse as if it exists. And if the inverse does not exist, then we know what that means. That means that you're not able to row reduce the matrix into the identity matrix. You know, the row reduction will just stop. And if it stops, then it means there is no inverse matrix, and then it's over. So whether or not the determinant is 0 or non-zero will not actually affect the process of finding the inverse. So this is not a requirement. So, and also to add this, row reduction generally takes n cubed steps to calculate, whereas determinants take n factorial steps to calculate. That's the reason why we turn a determinant problem into a row reduction problem, which takes, this is a much smaller number. Now, if you do 5, like if you do, for example, like if you just compare 5 cubed with 5 factorial, this is 125 and this is 120. So you could maybe make the argument that calculating the determinant of a 5 by 5 matrix in general may be faster than row reducing, finding the inverse of the matrix, which is 5 by 5. But this is the last time this number n cubed is bigger than n factorial. By the time you get to 6, 6 cubed is 216, whereas 6 factorial is 720. That's much bigger. And then from that point on, determinants are never effective at doing these kinds of calculations anymore. So the reason why this is important, if you're wondering, if it's ineffective, you might ask, if this theorem is computationally ineffective, then why is it important? Well, that has to do for theoretical reasons. So it is important for theoretical reasons that sometimes you're solving linear algebra problems and you know for a fact you want the determinant to be equal to 0. We're going to see that. We want something that becomes non-invertible. And in that case, we have to look for 0 determinants. So in that case, it becomes useful. But as far as a computational device by itself, that's not very effective. So I wanted to finish with the last thing. This is the last thing I wanted to finish with. So let's finish with this. So let us finish with the justification that the determinant of A is equal to the determinant of A transpose. I told you that this is a nice fact to know, and I want to explain to you what it has to do with. So here's an outline. Here's a proof outline. I'm going to give you the ideas of how to do it, and if you're interested, you can carefully check all of these facts. It's actually not that obvious why these two have to be the same. But, okay, so let's say as this, we can assume A is an invertible matrix, because otherwise the left-hand side and right-hand side are equal to 0 anyway. If the matrix is not invertible, then its transpose will not be invertible. And then this is 0 and that is 0, and then you're done. Okay, so you can assume the matrix is invertible. Now, because A is invertible, it means we can factor A into a product of elementary matrices. This is something we've talked about in the extra credit class, that you can factor A into a product of elementary matrices, like this. Now, this is what you have to check. You need to verify, you need to check that if E is an elementary matrix, then the determinant of E and the determinant of E transpose, or should I write like this, E transpose, are the same. It's actually easy to see. I'm going to leave the details up to you, but for example, let me just illustrate for you, maybe with a 3 by 3 matrix, why this works. So so if you start with the identity matrix, 1 0 0 0 1 0 0 0 1. Let's see what happens if we swap these two rows. We get an elementary matrix. So we would end up with 1 0 0 1 0 1 0 0 0. Okay, let's suppose this is our elementary matrix. If you take the transpose of this elementary matrix, you would get 1 0 0 0, 0, you will actually get the same thing. You notice that you actually get the same thing. The transpose is the same thing. If you have an elementary matrix like this, if you have an elementary matrix that is obtained by swapping rows, then it's actually a symmetric matrix. It's equal to its transpose. So then not only is the determinant of the matrix equal to the determinant of its transpose, the matrix is actually its transpose. So there's nothing to do here. Then the other one that you have, what's the other one that you have? Another type of elementary matrix you can have is an elementary matrix where you multiply one of these rows by some scalar. So let's suppose you multiply the third one by some scalar a. So that's going to be your elementary matrix. Well, again, it's a symmetric matrix. If you take its transpose, you would get the same thing. So you're not changing anything. So not only is not only are the determinants the same, but the transpose is the same as the original. So the one thing that's a bit trickier to see, it's not so hard, but it's a bit trickier to see, is what if you apply the row operation of adding one row into another column? So let's suppose the row operation here would be that we're adding a factor of, let's suppose, 3 into the second row. Then the matrix will look like this, okay? Then the elementary matrix will look like that. Now, if you take the transpose of that, you're actually getting something that is different. If you take the transpose of that, you would get something which is like this. No, sorry about that. You would actually get something which is like this. That's what you get. So the 3 gets moved over here. But it actually does not matter, because a matrix like this, its determinant is equal to 1. Because you only have to look at the diagonal. This one is upper triangular, this one is lower triangular, but the determinant of this one is, so even though in this case, in this type of elementary matrix, the matrix is different from its transpose, but the determinants you can see are actually the same. They're both equal to 1. So what does this mean? So here's the way you prove it. So the way the argument goes is, we said that A is equal to a product of that matrix, and now take the transpose of A. When you take the transpose of a product, that is the product of the transposes written in reverse order. So it's the transpose of this, it's the transpose of k minus 1 to the t, it's E2 transpose, E1 transpose. And now take the determinant of A transpose. So if you take the determinant of A transpose, using the property that the determinant is multiplicative, that's going to be the determinant of EK transpose, the determinant of EK minus 1 transpose, the determinant of E1 transpose. But we just said that the determinant of an elementary matrix and its transpose is the same. So this is the same thing as the determinant of EK without the transpose, the determinant of EK minus 1, the determinant of E1. But because these are numbers, these are no longer matrices. These are no longer matrices. These are now numbers. Because these are numbers, numbers can be rewritten and multiplied in the opposite order. So this is the determinant of E1, the determinant of E2, all the way up to the determinant of EK. But by using the multiplicative property of the determinant, that is again the determinant of E1, E2, up to EK, but we said that the determinant of that product of elementary matrices is the original matrix A. So look at how we started and how we finished. The determinant of A is equal to the determinant of its transpose. That's how we finished. So that's a nice argument. I mean, you get to see the advantage of how these elementary matrices can be beneficial for demonstrating something like this. But like I said, this transpose property, it just feels like it should be easy to show. It's actually not that easy to show, because, I mean, if you think about it, the determinant of the matrix, it's like a product of certain numbers multiplied together. When you take the transpose, you're just changing. I mean, even though the numbers are the same, the numbers that you're actually multiplying are going to be completely different. you can try that. I mean, just take like a 3 by 3 matrix and take its transpose and start multiplying out the numbers. The actual product of the numbers you're going to be multiplying, they're going to be different. But in the end, you end up with the same result. So that's what's going on over here.